Welcome to our video tutorials for our PC tool openSYDE. In this video, we would like to introduce the subject and take the first steps with openSYDE up to flashing a controller and the visualization of data. openSYDE is STW's software platform that supports you with various functions as a developer in application development for a system of controllers, as a person responsible for testing or production, or as a service employee. In this tutorial, we demonstrate the most important functions of openSYDE at a glance. Further details can be found in other videos in this series. What is openSYDE? openSYDE supports various activities over the entire product lifecycle. The focus is on application development in the system and design implementation phase. Many openSYDE functions are also applicable for updates, tests, automated end-of-line production, and maintenance tasks. openSYDE not only focuses on a single controller, but can also process a system made up of several controllers, devices, and bus systems. In this example, the system consists of 2 controllers, 2 CAN buses, and 1 Ethernet bus. The developer can now start the development environment for application programming from openSYDE by clicking on the corresponding node. With openSYDE, configuration and communication data about all components of the system can be conveniently recorded in one place. These recorded data also form the basis for generating source code, which means generating code in various programming languages which make manual entry of these parts of the code in the development environment obsolete and can be used immediately for programming the application. At STW, we talk about openSYDE being open. Open refers to 2 different areas. On the one hand, openSYDE has open interfaces, which means it enables the import and export of standard file formats such as DBC, EDS, and others. For documentation purposes, all entered data can also be output as an RTF file. All openSYDE projects are stored in XML format. On the other hand, openSYDE is an open source project. This means that the source code of our tool is open, and thus our customers have the opportunity to develop their own functions for the program. The source code is published on GitHub. We differentiate between different license models for the openSYDE core, which represents the actual functionality of the openSYDE tool, and for the graphical user interface. STW provides software for customers via the cloud. The openSYDE PC tool can also be downloaded there. You can find the link to the cloud in the manuals for our controllers, or you can get it from our support organization. We have published the source code on GitHub. This very extensive package is not required to use the tool, only if you want to develop your own features for openSYDE. All versions published so far can be found on the cloud. Usually, you are using the latest version. In the release notes, you can read about what has essentially changed since the last version of openSYDE. You will only find the executable tool on the cloud. So we download openSYDE from the STW cloud. The package can be installed on Windows PCs. The installation is a pure copy-paste installation, which means that you can save the package anywhere on the hard drive. The only condition is that you have full read and write access to the directory. The tool is located in the subdirectory Tool. You can create an icon on the desktop for your own convenience. Now let's take a closer look at openSYDE and start it. openSYDE is structured in projects. This is why the corresponding functions for new project, Open Project, and Saving a Project can be found on the Start page. In addition, there is a menu for creating a password-protected service project with restricted access rights. If projects have already been created and edited, openSYDE starts with the last edited project and shows this as the current project. A list of all edited projects can be found in the Recent Projects list. A project can be quickly restarted from this list. openSYDE is basically divided into two different areas. On the one hand, the system definition, in which we describe our system. This means we define a topology of the controls, bus systems and other devices used and describe their properties and communication with one another. In the system definition, there are also functions for generating source code in various programming languages, which facilitates application programming. On the other hand, there is system commissioning. The functions for flashing controllers, visualization of variables and bus signals, monitoring of data traffic on CAN buses, and so on are located here. The prerequisite for the use of these functions is the complete system definition and a successful connection of openSYDE to the system via CAN or Ethernet. For openSYDE, there is a user manual in the form of an online help which can be called up via the question mark. Before we continue with the functions of openSYDE, we want to build a real system containing a controller and a temperature sensor as an example for this video tutorial, and then process the system with openSYDE. We use an ESX3CS from STW as the controller. On the CAN bus 1 of the controller, we connect the required terminating resistors and a peak CAN USB interface for the connection of the PC on which openSYDE is running. We also connect a temperature sensor that has a CAN interface to the CAN bus. Finally, we connect a power supply unit to the inputs of the power supply of the devices. So we first have to describe the system that has just been built in openSYDE and create a new project to do so. openSYDE then jumps immediately to the system definition and here to description of the topology. A blank sheet is presented for the topology and a toolbox with STW devices that have already integrated openSYDE is displayed. By the way, with the F1 key you can call up the appropriate page in help for the respective function in a context-sensitive manner. The toolbox also offers placeholders for any devices from other manufacturers, so-called third-party nodes. It is also possible to create so-called user devices in the toolbox yourself, if you have the necessary device descriptions. We will now start creating the topology and start with the controller. In our example, an ESX3CS is dragged and dropped from the toolbox onto the sheet. Next, we need a CAN bus, which we draw onto the sheet in the same way. We connect controller and CAN bus. In our example, the CAN 1 was used, so we select this interface. We assume that openSYDE does not know the temperature sensor and therefore introduce it as a third-party device. We connect it to the CAN bus in the same way as the controller before. Our example consisting of the controller and the temperature sensor is now completely recorded. Next, the properties need to be described in detail. Let's start with the controller. With a double click or with the right mouse button, we reach the page for editing the properties. We have the options of changing the name of the controller and adding comments. In the name of the controller, certain characters such as spaces are not allowed. In the configuration section, the selection options depend on the device. In our example, with the ESX3CS, there is no option for protocol support or programming support, as this controller can only be processed with openSYDE. The generation of source code was also possible from the start with this controller. This is why programming support is also enabled. The STW controllers ESX3CM, 3XL and 3XM have the option of communicating via the openSYDE protocol as well as the KeyFX protocol. In this case, the options in the configuration section change. Next, we edit the communication interface settings. This controller has 3 communication interfaces, CAN 1 and 2, and an Ethernet interface. We can assign the node ID for each interface. openSYDE has already assigned the node IDs starting at 0 for the devices connected to the bus during the system definition. Our controller has the node ID 0, our sensor the node ID 1. If you try to assign the node ID 1 for the controller, openSYDE shows by the red representation that this would not be allowed. In case you continue with the wrong configuration, openSYDE will clearly mark this error. If you move the mouse over this display, you get further information about the error, such as the double assignment of an ID here. For controllers with Ethernet interface, the IP address can be specified in addition to the node ID. As default, a valid address is specified, which is incremented in the last digit during system definition when using several devices at the Ethernet. If this device is used in the system, the IP address can be adapted here according to the requirements of the network. By default, all interfaces are enabled for the update, dashboard and routing functions. This means that via each of the 3 interfaces, the controller can be updated, which means it can be flashed, can exchange data for display in dashboards and widgets, can be used for routing, which means that, for example, another controller can be flashed via the interfaces of this controller. These specifications only apply to the openSYDE PC tool. This information is not stored on the controllers. The data blocks are used to describe the application or applications that run on the controller. Initially, no data blocks are defined. To restore the factory settings of a controller, we can import the data blocks from the controller's target support package. openSYDE then creates the programming project with the sources based on the template project in a subdirectory of the openSYDE project directory. This also contains the hex file as a result of the project. However, we can also define data blocks ourselves and click on the plus sign to add a data block. openSYDE advises us that the project should be saved at this point in time. Now we can add the data block. We can assign names and comments for the data block. If the application is a non-programmable project, we leave the option File Generation Source Code option disabled. In this case, only the path where the project is located on the PC would have to be specified. Examples of such non-programmable projects are the runtime system of codices or the boot core application for the first processor core of the multi-core controllers of the 4th generation of STW. If we want to program the application ourselves and let openSYDE support us with generated source code, we activate the option File Generation Source Code. The files with the generated source code are created by a generator. A generator for the C code is supplied as standard by openSYDE, i.e. can be selected here with the default symbol. For other programming languages such as LogicAD, the corresponding code generator is delivered with the target support package of the control. Depending on the level of integration of openSYDE in the controllers, certain features are available. The required code structure version refers to this. More detailed information on the required version can be found in the controller's manual. A process ID is necessary for multi-core controllers. For the ESX3CS that we are currently working on, it is of no importance. Therefore, this entry remains 0. Code generated by openSYDE is provided in different files depending on the programming language. The folder in the file system in which the files are stored is specified here. The project path is preset to the path to the openSYDE project. You can specify this path relatively or absolutely. Output file refers to the result of a development project, which is mostly the hex file that represents the application. Name and storage location are specified here. For this video, I have saved a hex file in a directory as an example. In the field IDE call, you can store the command to start the appropriate development environment so that the IDE that matches the data block can be started from openSYDE. This concludes the data block definition. We can edit this definition again at any time. Now we can generate code for only this data block, and we can start the development environment for this project. Let's take another look at the details of our sensor. Since openSYDE cannot recognize third-party devices and therefore no protocol support is available, no data blocks can be defined for them. Therefore, no specifications can be made for the use of the interfaces for update, dashboard, or routing. Only the name and comments can be stored. Back to our controller. The properties of the controller and its application are described. We can now define data pools for the controller. With data pools, the developer manages variables, parameters, CAN communication, and information on the hardware configuration. There are 4 types of data pools. Diag data pools for creating variables and later monitoring their values. Entire lists of variables can be created quickly and easily with just a few clicks of the mouse. NVM data pools, which means non-volatile memory data pools, for creating parameters and storing them in the controller's EEPROM. Here too, the creation of corresponding lists can be done quickly. The HAL data pool fulfills tasks for the hardware configurator function, with which source code can be generated for the convenient use of inputs and outputs. Finally, the COM data pools for describing the CAN communication with messages and signals. In other videos in this series, we deal in detail with the HAL, NVM, and Diag data pools in connection with code generation and visualization. Here, we are initially only concerned with the COM data pool. In our example, we want to describe that the temperature sensor sends its measured values to the controller via the CAN bus. Sensors are usually delivered with an EDS file that describes the message and signals. Since these are assigned to the CAN bus, we have to import the information there. We can switch to the CAN bus via the navigation bar on the left. Here, we could create messages and signals manually, or we can just use the option to import the data from the EDS files. I have an EDS file for the temperature sensor used in this example. After selecting the file, I have to assign it to the device. A brief preview of what will happen during the import is displayed. The result is an imported message with the CAN ID 181. Since we have specified during the import of the message that it is assigned to the sensor, a COM data pool has also been created for it. No data pool has been created yet for the controller. Back to the CAN bus. You can see that the message has 2 signals. Clicking on a signal changes the view to the details of the signal. From the documentation of the sensor, we could see that the first 4 bytes contain the measurement result and the 5th byte contains status information. We can adapt the names accordingly. Since obviously only 5 bytes are used, we can set the data length code to 5. This message is sent from the sensor. To be able to mark the controller as the receiver of the message, we declare it to be an active protocol node and assign it as the receiver. openSYDE has now created data pools for the 2 devices. We can now assign the data pool of the controller to the data block, which represents its application. From now on, openSYDE can generate source code for this CAN message. We will deal with this topic in more detail in another video. System definition for our example is now complete. We can export this to an RTF document for documentation purposes and receive a structured project document with all entries in tabular form. After all definitions have been completed, the actual programming work begins for the developer. Generated code is created and integrated into the own programmed code of the application. The resulting hex file must then be flashed on the controller. For this we use the second work area of openSYDE, system commissioning. First of all, we can define the view of our system. After the system definition, a view number 1 with all components involved is created in system commissioning. Here we can also see the PC on which the openSYDE program is running and how it is connected to the system. In our example, the PC is connected with the same CAN bus with which the controller and temperature sensor are connected. For such a small system, of course, no other views are required, and we therefore use the existing view showing all components. If we want to edit the view, we click on Edit and can now remove devices from the view or connect the openSYDE client PC to another interface. In this case, we only have the CAN 1 available, therefore we leave the current view as it is. Let us imagine that the devices in our example were delivered fresh from the factory. Then the first task is to transfer all the configurations to the devices as we have defined them in the system definition. openSYDE offers a device configuration function for this purpose. This function is possible via all interfaces like CAN or Ethernet. The prerequisite, however, is that the real physical world corresponds to the view for the device configuration, which means when openSYDE calls up the device configuration, no more or fewer devices may report than are actually connected to the interface. The routing function is not permitted for the device configuration feature. Furthermore, the speed of the CAN bus must be the same and of course known for all devices. In order for openSYDE to be able to switch the devices to the respective operating mode, the openSYDE server must also run on the devices. This is the case in the delivery state of the controllers from STW. In our example, we know that the control and the temperature sensor on the CAN bus are set to a speed of 125 kilobit per second. The temperature sensor, as a third-party device, is not known to openSYDE in more detail. It is therefore not expected as a so-called topology node, and therefore only the controller appears in the list. We can now scan the network in the first step. We show you the real controllers live. You can see from the LEDs that the control is currently in an operating state in which the application is running without errors. After clicking on Scan for Devices, the controller is switched to flash loader mode, as you can see from the flashing red LED. If no application with an integrated openSYDE server was running on the controller, you could have the device recognized by switching the controller off and on after clicking on Scan for Devices. Our controller now appears in the list of connected devices. It can be clearly identified via the serial number. We now assign the device found to the device in our topology from the system definition. We transfer the configuration as stored in openSYDE by clicking on Configure Devices. This was successful. We can see from the report that the node ID and CAN bit rate have been set as required. These settings have also been verified. You can also see from the LEDs that openSYDE has reset the controller. This terminated the flash loader mode and the application is now running again. With the successful device configuration, the requirements for flashing the controller in the system are now met. The corresponding function for this in openSYDE is called Update. In this view, we see our system of controller and temperature sensor with the connected openSYDE client PC. We can see from the symbol that the temperature sensor is excluded from the update because it is a third-party device and the protocol is not known. The update package is available for flashing. This consists of the X file that we've stored in the data block for the ESX3CS. The hex file represents the standard. We can also select another hex file by clicking with the right mouse button or return to this setting with Revert to Default option. To start the update, we click on Enter Update Mode. openSYDE automatically puts all devices in flash loader mode, in our example, the controller. Again, you can recognize this by the LEDs. In flash loader mode, openSYDE can check whether the controller has already loaded the hex file from the update package. This is the case here in our example. By double-clicking on the controller, however, we can force the hex file to be flashed on the controller again. The controller is now displayed in such a way that an update is required. By clicking on Update, the flash process is started and the progress is visualized. The end result is again the updated controller, which remains in flash loader mode. Clicking on Exit Update Mode resets the controller and the update is finished. The system can also be updated on the basis of a command line command. The command is sides up. In this case, the user does not need the entire openSYDE tool, but only the sides up exe and the so-called service update package. The sides up exe is part of the delivered openSYDE tool. It can be found in the Utilities directory. A service update package must be generated with openSYDE. In the View in the Update area, the appropriate package is generated by clicking on the openSYDE symbol. Device descriptions, information on communication, and the hex files are packed together. In the Windows command prompt, we call up sides up exe with a few options which are described in the help. Now the system is updated without further use of the openSYDE tool, so here the hex file is flashed again on our controller. This feature can be used for automation, for example on a production line. On several dashboards, openSYDE allows various widgets which can display or set values. Elements of the data pools or bus signals are assigned to individual displays. In online mode, the values are exchanged between the dashboards and the system. As a demonstration, we want to display the measured temperature value of the temperature sensor. To set up the dashboard, we activate the Edit mode. The toolbox provides us with a selection of different display elements as well as information elements for design. To display the temperature, we need a simple reading widget to display the value. We drag and drop it from the toolbox onto the dashboard. OpenSYDE already indicates that no data element has yet been assigned. We can change this by double-clicking the widget. Data elements can either be data pool elements or bus signals. We use the CAN message with the temperature value of the sensor as an example. It is possible to adapt the display if the specification in the system definition are not to be used. With Confirm, we complete the editing of the dashboard. The connection to the system is established by clicking on Online. The temperature value is displayed. Changes can be observed live. The CAN monitor, integrated in openSYDE, is used to observe the data traffic on the CAN bus. The program can be called up via the corresponding button under System Commissioning. The program will open in a separate window. openSYDE CAN monitor has its own file management, which means that all settings for a session can be saved in separate projects and called up again. In the Trace window, the data recorded on the CAN bus is displayed and interpreted in various ways. In the Message Generator window, you can manually create CAN messages that are sent as single or cyclical messages to the CAN bus. For various features of the program, you can load databases that allow the CAN message to be easily interpreted or predefined messages to be written. The monitoring can be restricted to certain CAN IDs by filtering. The measured data can be saved in log files. The PC CAN interface can be configured for common CAN interfaces. The CAN monitor can be coupled with openSYDE projects. For this purpose, the entire system definition of an openSYDE project can be loaded into the program as a database. In addition to the openSYDE format, data in DBC format could also be used. If we now load the system definition from our sample project and start the measurement, we not only see the bare hex stream of the data, but also recognize in plain text, for example, the temperature value of our temperature sensor. We can also write CAN messages on the bus for simulation purposes. We can use the database again and here, for example, select the fully configured message of the temperature sensor. This message is of the on-event type. The cyclic transmission switch is therefore irrelevant, but I can write the message to the CAN bus with a manual trigger. To make this clear, we take the temperature sensor from the CAN bus, restart the measurement, and trigger the message manually. Of course, you can also configure your own messages manually, independently of a database. If cyclic transmissions is switched on, the message will be sent cyclically. Certain IDs can be hidden to restrict the measurement result. Again, we can use the database or enter certain IDs directly. With manual triggers, measurement results can be saved in log files. Each click on On opens the file and closes it with Off. The result is log files that are marked with a timestamp. By default, they are located in the logs subdirectory. The directory can of course be determined. The data stream is saved depending on the format selected. I hope to have brought you the basic functions of openSYDE a little closer, and you can now use them for your system. In the series of openSYDE videos, further videos will appear on this channel that deal with the details of single features. I wish you every success in using openSYDE.